Okay, well, really fantastic to be here. I love Async API. I came across it a few years ago and became a fan of all its possibilities and the amount of progress since then when I sort of just came across it in Postman Galaxy, and today with the full Linux Foundation and a huge community of volunteers, it's been a very inspiring thing to watch, and it's one of the most efficient, effective, and friendly, welcoming open source communities I've had the privilege of being involved in. So it's a great thing to be here with you all and to be learning for the incredible talks and to be sharing some thoughts. About myself, I am the director of the Adora Foundation, and I'm lead researcher right now at the Green Software Foundation, working on the State of Green Software report, and software engineer by background, also social entrepreneur, and very focused on sustainability, and particularly the role of tech and digital emissions on the environment and what we can do about it. And that's what led me to really begin to explore this delayed tolerant networking, as I will explore or explain in a minute. So delay disruption tolerant networks. When do you use them? You use them when messaging involves very high latency. Think Earth to moon latency. Or where there's very low data rate or a lot of disconnection, think the middle of the ocean, or limited connection range. I once lived in a very remote Maasai village, and they had phones, mobile phones, maybe 2 in the village. They had 1 cassette tape. I spoke about this in an earlier API, I think AsyncAPI conference, but they had very low connectivity. They weren't within range of Wi-Fi and similar. And so this is another use case. And then what is called time shifting in carbon-aware computing. So the electricity today is a mixed thing. It's mixed between dirty fossil fuel, coal burning plants and green, renewable wind and solar and hydro powered plants. And the problem with nature is that you have to be a partner. You're not really an owner or a controller of nature. So you can't really decide when the wind will blow or the sun will shine. And therefore, during any given day, the electricity will have moments where it's mostly powered by renewables or only powered by renewables, and moments where it's mostly or only powered by dirty energy. Time shifting involves making sure that your computing only happens at the times when the electricity is cleanest. And therefore, this notion of delay or disruption tolerance can be helpful. If your gadget or device is can process the information or receive the messaging at clean times and doesn't have to be on at all times, this will be another great value. So delayed disruption tolerant networking is an approach to routing messages in an asynchronous way, hence async API, and in an event-driven way, but in a way that does not require a direct constant link or range of connection. So it uses something called a store carry forward relay routing architecture. And I'll explore a bit more what this means in detail, but it's the idea that you don't just send the signal, you don't just send the signal, store it, and then convey it to your subscribers, but you can convey it to subscribers, which then carry it on to another area and hit subscribers in that remote area that are connecting not to your original source or your broker, but to that mobile device, for example. So it is used for the Internet of Things. It is used for vehicle-to-vehicle communication, for carbon-aware computing, as I mentioned, and areas where there is very low infrastructure. In hard-to-reach locations like outer space, mid-ocean, and remote regions, or in sort of easy-to-reach locations, but in circumstances that impose interruptions, latency, or delays. So this is a paradigm that I think we are pretty familiar with in event-driven architectures. The message goes to a streaming service, and the streaming services publish it to all subscribers within range at the time. So if that message is being streamed at 11, anyone who is connected at 11 a.m. will receive that message because it's just forwarding it on. The device number 2 that logs in at half 11 will not have received that original message. So it's like jumping in halfway through a terrestrial TV program. You are just hitting it at the point you're hitting it. So the previous messages are gone. Another paradigm that is very familiar is the store forward paradigm. So a queue is a good example. So the message goes into a queue, and then all of the subscribers will receive that message as soon as they connect to that queue. So it could be at 11 a.m. and then someone else comes at 11:30 a.m. and they get their SNS notification or whatever it is that you are relying. So here, your broker is not just forwarding, but storing. So the architecture is a store forward paradigm. Device number 3 is out of reach. It is never going to connect to that queue. And so it will never receive the message, no matter at what time it connects, because it will never be in range of that broker. And therefore, the store forward mechanism will never reach it. And that will be the case whether you are in the International Space Station or in a very remote village in Bangladesh or in the middle of the ocean in your cruiser. So store carry forward will send the message to your queue or your stream. It doesn't matter. I think it should say queue because I've got a device there at 11:30. So it's the queue, and it will send it to all of the subscribers that come on. So this device number 1 gets it at 11. Device number 2 gets it at 11:30. And there's a moving object, which is a device. It might not be an end device. It might not even be a kind of a destination device, but it will store the message and carry it. And when it's carrying it, it will now be in range of device 3 and transmit that message. So that device 3 never comes in touch with your broker, is never in range of the message, but it still receives it via that moving object that stored it, carried it, and forwarded. And this is a powerful paradigm in so many ways. So the internet, for example, requires all of the protocols to align in order to stream one message from your server to the end device, for example. And that can create an element of latency. With a store carry forward, you might just store the first layer until that second layer aligns with the next layer and not necessarily with the first layer. And that will mean that you can actually send a lot more messages in between in an asynchronous way. And that's why it is of such interest for interplanetary communication, which is where the paradigm started. So it began in NASA, it began in space research, it extended with DARPA into defense and therefore into terrestrial applications. And then it went beyond defense and space into all kinds of uses where these paradigms are useful. So there are a number of relay strategies that do not necessarily reflect this kind of streaming API from Twitter to the browser. So instead of just that direct communication, your intermediary objects, that moving object in between, it could be an opportunistic relationship. So if the browser is entirely out of reach of Wi-Fi, for example, it may be that you are relying on that moving object is a random mobile phone, and you don't know which mobile phone will be in range when. So this is an opportunistic relay. You're basically looking out for any device that is willing to carry your message, and sort of you'll send it potentially to lots of devices, all of the devices there, so that they in turn opportunistically relay it to end devices that happen to be along their route. Or it could be a cooperative relay strategy. In this case, you have very specific devices that are cooperating. So you're not waiting on a random mobile phone. You know that there is going to be a train passing at the same time every day in the same place, and that train will be passing through a neighborhood that has no connection to the internet normally, but will be in range of that train for just enough time for that train to receive that Twitter message. There's probably more important things you can do with it, but that's just one example. So here you have a cooperative relay strategy where those machines are consciously cooperating with you to send it. And finally, you could have a competitive strategy where there are perhaps some time pressures or perhaps priority of messaging, etc. So you might have 5 potential machines that are collaborators that you know are going to go there, and you send it to all 5, and the one that gets there first transmits it. It's also not all or nothing, for example. It could be that part of the message is streamed by that first train, and the last part of the message is streamed by a sort of drone that is passing, etc. So there are many architectures that you can create depending on your use case, and people have created sort of a mix of all of this, where you use opportunistic mobile phones, but you also have relay boxes in between, so that the mobile phone transmits it opportunistically to a relay box that cooperatively transmits it to another relay box, where you potentially have a central point that treats different relay boxes in a competitive way. And this is, for example, a use case in disaster communications, where you might have sort of emergency services with their own backup communications infrastructure in the middle of nowhere. And they are integrating multiple streams of information and then communicating an integrated narrative back to headquarters. So there's a lot of possibilities around these. So I mentioned here a few examples already. Now, this is important. For example, at the moment, most of our Internet of Things is very energy and communications dumb. It is basically on all the time, even if it only needs to be on for a particular moment of time. And that means that it is generating digital emissions. It is burning through battery when it might not need to. So being able to identify which connected devices could be delay tolerant is hugely important. Likewise, connected devices are very often mobile, and therefore being able to identify which connected devices could act as carriers for signals and therefore bring in our messages beyond those people who get to connect in range of whatever infrastructure we are using to communicate, again, becomes quite instrumental. So designing connected devices that can both be delay tolerant and also act as carrying relays, both for messaging that is directly relevant to them. So it might be that you have a watch that requires to receive messaging for all of the apps that are running on its smartwatch. But it could also be that you are an altruistic, that I forgot that paradigm. That's another paradigm, is altruistic delay tolerant network. So your phone, for example, your watch, for example, might agnostically say, I am happy to take messages in general. And there's thought around security that has been going on, and in fact, it's been sort of built into a lot of the networks from the start. It might be that it's a subsection of signals that you're open to, but essentially you are saying, I'm open to signals that don't benefit my user, that benefit third parties, and my user is happy to use his watch for that. So that's another way in which connected devices, Internet of Things, would be using this paradigm. Vehicular networks, vehicle-to-vehicle communication. This is something that is growing in significance as IoT, as electric vehicles, as smart cities, smart networks. All of this ecosystem is accelerating and does seem to be the face of things to come. We are not yet at a point of having reached critical mass. So a lot of this vehicle-to-vehicle networking is still at the proof of concept stage. But in whatever scenario we are looking at, then delay tolerant networked communication and routing has a potentially very big role to play. So the idea would be that a car, for example, that is coming in the opposite direction from you will have information about traffic conditions ahead of you. And so that car could communicate with your car to transmit that information, which in turn is aggregating the input from that car in the opposite direction with all the other inputs it has access to and transmitting them to other cars, which means that the level of detail and richness that you can get in terms of road information is incomparable in relation to what we have today. So this would make self-driving cars, for example, inconceivably more safe and accurate and powerful. And there are, of course, non-vehicular advantages to being able to create such dynamic mesh networks between cars. Carbon-aware computing, I have already sort of mentioned it. So this could apply to your connected devices, to the Internet of Things, or it could apply to your software. So if a particular process, or more specifically in our case, a particular subscription to a message is not time sensitive, then you could describe your APIs in such a way that that transmission only happens at times when the electricity grids, both in the emitting, the publishing side, and the consumer subscriber side, are at their greenest. So if you could create a set of APIs that communicate with each other, not just in terms of their task, but also in terms of, for example, their level of battery, but also in terms of their emissions and the grid and the local electricity conditions. This could be a game changer to the gigantic contribution that our sector is making to climate change, and where most other sectors are gradually diminishing their contribution to climate change at the moment, not fast enough to avoid really painful scenarios, but decreasing. Our industry, the digital technological industry, is still growing. So the data that we're using is growing. The electricity we're consuming is growing. We are becoming more efficient, so we are consuming less energy per process as time goes by. But our growth is so extensive that our net emissions keep on growing, even if we become more efficient. So being able to be carbon aware in our devices and describe that in some way and ensure that our communication imposes delays as opposed to tolerate delays, welcomes delays, embraces delays, but does so in a way that is coordinated and that allows us to essentially run on green energy, which will give us more and more availability the more and more we green the our energy consumption globally, then that's fantastic. And finally, I have mentioned examples of low infrastructure. This is a case for digital inclusion. At the moment, in spite of this tremendous mark that we're making on the world positively and negatively, 50% of the planet is not connected. This is huge. And given what happens on the internet, what happens in digital life, that digital exclusion is a financial exclusion, is a knowledge exclusion, is a gigantic injustice. And at the moment, our approach to reaching those hard to reach areas, to connecting those disconnected areas, has tended to be, we just have to grow more, which of course is going to create even more problems for those areas, as they are the main sufferers of the impacts of climate change. So delay-tolerant networks are a paradigm that allows us to envisage ways of creating connectivity in areas of the world that are currently excluded from the digital conversation, without necessarily having to think about investing in major infrastructure projects in every single area and major servers and all of these things. So being able to create more distributed processes is that next civilizational step, as it were, that I described in my last AsyncAPI talk, this sense that we are moving toward a much more nuanced, reactive, distributed, event-driven society, and not just technology. So what are the cases for AsyncAPI in delay and disruption tolerant networking? As far as I have been able to tell, I haven't come across any use of AsyncAPI in the delay tolerant networking community. And this is a pity on both sides. I think that AsyncAPI has a huge role to play in the paradigm that I've just described. AsyncAPI, of course, is there to describe event-driven communications. And delay-tolerant networks are quintessentially event-driven routing protocols. Moreover, AsyncAPI is protocol agnostic. This is absolutely critical because at the moment, we are at risk of a proliferation of protocols. And there will be a proliferation of protocols. Delay-tolerant networks in the Internet of Things will use different protocols for different types of Internet of Things, different protocols for vehicular communication, different protocols for interplanetary communication. So this is on the one hand natural, and it makes sense. You might not want to use the same protocol for your smartwatch as you are using to communicate with Mars. But on the other hand, it also creates a huge amount of complexity and constraints, because one of the key promises of the store carry forward paradigm is interoperability, is this idea that my watch or my mobile phone or my car could help deliver emergency services information in a massive flood or heat wave or earthquake to emergency services and to sort of the central coordination side of the government. And if all the protocols are not able to talk to one another, our ability to do this is hamstrung. So being able to have a language to describe our APIs that is protocol agnostic, that allows my car and my watch to talk to one another and to the emergency services and to the International Space Station as need arises, is really powerful and really significant. And being able, particularly when we're talking about, for example, opportunistic or altruistic routing strategies, being able to say, I am open to these kinds of signals, I welcome these kinds of APIs, and I am transmitting these kinds of APIs and these kinds of messages to these kinds of servers, this is really important. And at the moment, as far as I'm aware, and I'm certainly not an expert in this field, but as far as I've been able to tell, there isn't anything like it. There is no way, there is thought going on into creating common standards, and there is work going on into thinking about this interoperability, but not in a protocol agnostic way. So AsyncAPI offers to the delay-tolerant network community the ability to talk to one another, not just now, not just for uses they already foresee, but for the future, for all the uses and all the applications that are emergent, that will become possible and that no one can predict, because that is the nature of an event-driven society, that we are using and collaborating and harnessing information from one another for uses that we never thought of before, and that the aggregation of previously unrelated information makes possible innovations and applications that people would not have been able to even conceive or imagine before that data or those information streams could be aggregated. So AsyncAPI provides a language to be able to aggregate these kinds of communications and informations and innovate and expand. And because AsyncAPI has been working on this fantastic tooling, some of which we've had demoed and highlighted in this fantastic conference and will continue to have, therefore, the delay-tolerant network community can also greatly benefit from advances in this tooling to simplify and shorten the amount of work involved in the processes. Most of the delay-tolerant network community, as far as I've been able to tell, tends to be much more hardware-focused than software-focused, and infrastructure-focused than software-focused. And that means that if they had software-focused tooling that could accelerate and improve the quality and the interoperability of the hardware they are building, this is surely a massive win. And in addition to the interoperability aspect that I've mentioned, I think another thing that AsyncAPI can offer the delay-tolerant network community is the possibility of design-first approaches and specification-first approaches. If people already know what the entire data structure and what the entire communication protocol and what the requirements of communication and interaction will be for a particular technology, then an entire ecosystem can already start building knowing that that will be in place, and purely on a combination of the AsyncAPI spec and its tooling. And that will accelerate innovation, and again, in ways that are potentially unpredictable. So if I can read the AsyncAPI spec of the next Samsung smartwatch, I might already know that I would be able to use it for emergency services in conditions of disasters, for example. And I might be able to reach out to the Samsung team and say, hey, this is what we're thinking. We are sort of the United States government. We'd like to be able to do something like this. This is our async API spec. Would you like to talk? So the possibilities that design first makes possible, not just in terms of speed to market and defect reduction and all of the values that we already know about, also has a potential in terms of the innovation and collaboration process that this very innovative and networked ecosystem is having and will have. So this brings questions with it to us. Can Async API, as it stands, describe effectively the store carry forward routing strategies? Can the Async API tooling be used for delay tolerant networks? Is the existing spec fit for purpose, or could it benefit from extending? I will not fully answer these questions today. If anything, I think that the main contribution I would like this talk to make in terms of the audience here today, which is Async API practitioners and experts, is for you to take these questions forward. I will obviously give it a stab, but really I think this is something that can be explored a lot more. And this is something where I think if the Async API initiative were to create, for example, some good thought pieces, some good materials that the delay tolerant network community could get hold of, ideally collaboratively, ideally with someone from that community, from whether it be there are some massive networks now outside of just NASA and DARPA, etc. There are equivalents of the Async API, as it were, initiative, non-profit foundations that are having this conversation. So I think if there could be the kind of conversation and documentation that would put this on the radar of this sort of very important part of our emerging technology landscape, this would be huge. So I hope that this awakens the curiosity of some of the people here today to explore this further than I will. Now, looking at this from a sort of a very introductory perspective, and I won't dwell any in detail. You can see I'm using the 2.0 here from the slide, and we are ahead now. So I think the presentations that have been given today and that will continue to be given will sort of flesh this out a lot more. But at a high level, I think this provides, in my view, what you need essentially to describe the core of a delay tolerant network of a store carry forward protocol, because you are saying this is what this application is. This is a store carry forward, and it is being served from here. This may need perhaps a bit of refinement, because obviously if the carry portion of it, that vehicle that has taken the message with it, my understanding is that here it would become the server essentially, because it no longer has any connection to the original server, and it is emitting the message that it is carrying for its publisher and subscribers. So how would you describe the servers is something I would love your input on. Is the server purely the originator? Do we have our sort of, production staging, and along the same lines, would the carrier sort of inject into the server description its own self? I'm not sure, but sort of that's where that would go, right? And then, of course, you have your channels, and sort of that again is fairly straightforward in principle, because essentially every carrier of messages is both a subscriber and a publisher, and essentially a broker, really. And components, I think, become particularly valuable in this paradigm, insofar as they might be reusable cross-device, cross-application. There might be components that can be reused by a whole range of completely independent connected devices, for example, which are intending to talk to one another as part of their protocol. So it might be that the components part of the specification gains importance within specific domains in the delay-tolerant networking world. So, if you are using delay-tolerant networks for communication with voice at sea, then it might be that even if the manufacturers of each of these devices are completely independent, they might use certain common components for their async API descriptions to maintain interoperability and facility and this design first approaches. Now, the channels, again, I think my intuition, my instinct is that they are good enough as they stand, because you are able to say, I subscribe to these operations as a carrier, for example. I'm focusing on carriers because I think the other components in my diagram are already being used by AsyncAPI, and we know they work. But it's these temporary mobile carriers that are not just publisher and subscribers, but also brokers. But my understanding is that really a broker is still essentially a publisher and a subscriber. So they would presumably have to specify what they subscribe to in order to be able to carry that original message from the broker, and what they publish, and what are the what is the data formats that they publish. And this could potentially be really quite complex. Again, an area where components come into their own, because if you are acting as a carrier potentially for things that you are not going to consume, you don't really care about the data format yourself. You're just passing it on for anybody who happens to use that data format. So again, this is where components could become really valuable, because you might say, I am a publisher of this component. I am a publisher of this component. I'm a publisher of this component. And each of those components might have completely different data structures and payloads and headers, etc., in accordance to the multiple protocols that that carrier may or may not interact with. And so yes, I think I've already mentioned here. And here you have, when we look at the components, you have the schemas, the messages, the security schemes, and the bindings. I think my understanding of bindings is that bindings are the protocol-specific requirements, the requirements that you wouldn't say in a generic async API, that are specific to one particular system that will be using your protocol. So I think this is probably one of the most crucial elements where thought needs to be given. So these are perhaps this is the place where you specify, for example, whether you are carbon aware, whether you are going to be operating, publishing only when your electricity grid is clean, or, sort of accepting subscriptions only when you hear that the electricity grid is green from your subscriber, for example. I'm not sure, but I do think that this is the area, the bindings area is the bit that makes async API so usable already for delay-tolerant networks, because anything that is not covered in the async API specification can be added to the bindings and to the extensions. I think this is very important for those who might be listening to this presentation and are not aware of extensions, the fact that you can take the async API spec and extend it for your purposes. And my understanding is that in the community, the async API community, you might often begin with extensions, and if some of those extensions prove to have really general value and not just for the people who extended it, they might sort of become part of the next universal async API spec. And this is a real opportunity, again, for people in the very emergent, very new, very fast-changing delay-tolerant network space. Because if there's something that is missing or does not quite fit in the current async API spec, and that is not handled in the binding section, then you can always extend it. And it might be that when one of these store carry forward implementers extends it in some way, you have, 3,000 delay tolerant network products saying, me too, please. And that becomes sort of either stays as an extension, becomes mainstreamed into the async API spec. So I think sort of my summary of this would be to say that that I think we have enough now for proof of concept. I think we have enough now to use async API to describe delay-tolerant networks and store carry-forward protocols. Do we have enough to describe all store carry-forward protocols? I'm not sure. Do we have enough to be the best use case for all delay-tolerant networks? I'm not sure. This is an area where I really hope this starts a conversation. And more generally, is in this example, for example, without thinking just of the store carry forward protocol, when we're thinking about the carbon aware computing, which is growing and growing and growing and will continue to grow, where would be the best place to do this now? Would it be in the overall in our sort of description, in our extensions, in our bindings, or is this something that should become part of the async API spec, some form of signaling this carbon-aware sensitivity to different devices? That's my last question. So thank you very much for having me, and I look forward to whatever conversation ensues.